Okay, if you want to copy down, this is known as the magic formula. So I don't know if, when we calculate the Mohr-Cartan form, remember u goes something like e to the I x dot pi. And the question is, what happens if these x's don't commute with each other? Okay, so this is a beautiful little formula. In other words, if I take this derivative, then d mu pi projected onto x may not commute with pi projected onto x in general if the x's don't commute. Right? So how do you evaluate this object? So in the cases where all the x's commute with each other, it's really simple, because when you take the derivative, you're free. You can put it down on the left-hand side of the exponential. You can take the derivative and put it down on the right-hand side of the exponential, right? But what do you do if they don't commute? You have to be more careful. And so you use this formula here. And in order to derive this formula, you start with this formula. And then you use this is the Baker-Campbell-Hausdorff formula. You've probably seen it from quantum mechanics. This is BCH. Then once you have these two, then this one follows sort of trivially, just by expanding the exponential and doing the integrals, right? So if you want to entertain yourself, try to prove this. It's non-trivial, and there's a trick involved. So, I'll tell you how to do it before the end of the week, or maybe Duff will tell you how to do it. But it's a fun little thing to do. Okay, if you don't want to prove this for yourself, but at least this formula you'll need, so if you do SON, breaking to SON minus 1, since the generators don't commute with each other, you've got to figure out how to, so in order to do this exercise, remember what we said yesterday, you extract the covariant derivative, right? And in order to extract the covariant derivative, you have to be able to write down the Mohr-Cartan form, and in order to do that, then you have to know how to calculate this, but in order to do that, then you should use this formula here. Okay? So this actually is not a lot of calculation. It's only like 3 lines. Yeah? Yeah. So no. So this is little x. This is the function little x. This big x are the generators. And this derivative just acts on the pion fields. Okay. Okay. Are there any questions from last time? So I was hoping someone would ask me a question about locality and the way I defined it yesterday, because there's a subtlety. Can I erase this now? Did everybody get this? So let me write down an action for you. And you tell me if you think it's local or not. So I can either write it down in X space, or I can write it down in momentum space. Okay, so that should look vaguely familiar to you, right? That's the Coulomb interaction between two charge densities, rho of x, rho of y. So that's non-local. So if you go into momentum space, it just becomes like 1 over q squared, which clearly doesn't have a well-defined limit as I defined it. So there are 2 ways to tell if something's non-local. One, Equivalently, if you have something which doesn't have a well-defined limit when q goes to 0, you can always write it as a convolution in two variables. So if you were to Fourier transform this back into momentum space, you would see this. So you could see also physically this is non-local because this is giving you interaction between x and y instantaneously, right? So it's action at a distance. So this would seem to be a problem. So it seems like I'm telling you that electrodynamics is non-local, right? But we know that's not true. Okay? So the other way, this is electrodynamics in the Coulomb gauge where you eliminate A0, right? So there's a caveat to the statement. When you look at an action, can you really tell if non-local just because it looks non-local? And the answer is no. Okay? There's sometimes it's possible to change variables and to take something which looks non-local and make it local. So there's no magic way to determine if theory is local or non-local or not. There's no sort of algorithm. If it looks non-local, it probably is non-local, but it's not necessarily, and you have to look to see if it's non-local by seeing if you can perform a change of variables, right? So if you have a theory that has an interaction that looks like this, then we know we could rewrite it in terms of a coupling between rho and A0, right? In other words, this comes from an exchange of a photon. And all I've done is to use I've eliminated the photon by using the equations of motion for A0 in the Coulomb gauge, right? Because the A0 is a non-dynamical degree of freedom, and I can just use the equations of motion to eliminate it. And what I've done is I've eliminated it, and I've generated an action which looks non-local, because this looks like it's generating in Fourier space rho of q, rho of minus q. Remember, rho is psi dagger psi, psi dagger psi. So it looks non-local, but it's not, right? Because there's a way of writing it in a local way. So there's no magic way to tell when just staring at something whether or not it's local or non-local. But this is a sort of a separate class that we don't really have time to go into, where you can actually do some work and figure out whether or not something's local or non-local by trying to understand the non-analytic structure of the scattering amplitudes. But we don't really have time for that, and that's more a quantum issue. But okay, does everyone do you understand that? What I meant? What am I trying to convey here is that you have to be careful. Okay. So in general, it's true that if someone hands you an action that doesn't have a well-defined or has non-analytic structure in the action in momentum space, then it's going to be non-local. But there are exceptions, and I just gave you a very simple example of that. Okay. Okay, so we left off discussing internal symmetries in the Coset construction, and sort of the magic formula, which relates how to extract objects which have well-defined H transformation properties, such that given a Mark-Cartan form, one can extract out the relevant quantities. So this is for internal symmetries. We said we can extract out the, I'm not sure if I wrote big, I think I wrote, Did I use big D or nabla? I think I wrote Is that how I wrote it yesterday? I think I'm trying to remember what notation I used. But the coefficient of x was a covariant derivative, and the coefficient of t is transforms like a gauge field. And so we said we can write down an action, say that looks like this. And then I can write down more and more terms, and then these terms will be down by powers of the scale at which the symmetry, which the theory breaks down, namely what we call the cutoff, or the value of the order parameter, the scale which breaks the symmetry. And I just wanted to say a little bit about this A mu, since it's going to show up. So how do we use A mu to construct invariance? So suppose there's another field in the theory, say a massive field that I want to couple the pions to. So for instance, nucleons, if I were doing a Caylagrangian. And this psi transforms linearly in G in the full group. Now we want to build H invariance. We know how these things transform under H, and this thing is transforming under G. So if we want to combine them, we've got to do some work, because psi is transforming under G, and our geometric objects are transforming under H. Right. So remember, under a G transformation, our geometric objects are transforming covariantly under H. Right. So under psi, under a G transformation goes to G psi. So the trick to writing something which transforms linearly under H is to define a psi twiddle as being equal to a u of pi times psi. Then under G, so psi goes to G u of pi, so psi twiddle goes to G u of pi psi, right? But we know that G u of pi is u of pi prime times H of G and pi on psi. Okay, so let's see. So I'm sorry. So psi under a G goes like this, right? So this is psi twiddle, right? Is that right? So G, I'm missing a -1 here. Yes. Okay. So this goes to some other u times H on psi. And so we can call this u of pi prime on psi twiddle prime. Okay? So what we've concluded from this is that psi twiddle under a G goes to H on psi twiddle. Okay, so now we have something which is well defined, whose G transformation gives us an H transformation. So now we have a whole bunch of objects which transform under H, and now we can form an invariant. Right? Yeah. Here. This is the transformation property. H psi tilde. Yep. Thank you. Okay, so how can we use now? The point is, now if we want to look at a derivative operating on psi, right? So we want to, if we take we can define a covariant derivative on psi twiddle as just being equal to d mu psi twiddle plus a mu a ta psi twiddle. And now this thing will transform covariantly under H, right? So remember that this H in general is going to depend on the pion fields. So even though psi twiddle transforms nicely under G, forming an H transformation, the derivative won't, right? But the A mu is exactly there to fix. This is just like a gauge transformation in QED. Right? This H is like a gauge transformation, and the d mu will hit the H, but that variation is exactly canceled by the variation in a mu. Right? So now I can form a H invariant, say, by squaring this. Will be a Lorentz invariant, H invariant quantity. Okay? Okay. So now what we're going to do is we're going to shift gears for a little bit, and actually for the rest of the way, and talk about the breaking of spacetime symmetries. Okay? Any questions of this before I move on? Okay, so what makes space-time symmetries a little bit more interesting is that the group is no longer compact, right? Because the translations and the boosts are not compact subgroups. So we have to modify what we're doing in order to account for the fact that that the symmetry is no longer compact. So that means, so I didn't prove this to you, but yesterday we said that if a group is compact, then the symmetry generators can always be chosen in a basis such that, not the symmetry, I'm sorry, the structure constants can be chosen in a certain basis to be totally antisymmetric. And we use that fact to show, so remember that, so T with T is a T. And we use that fact to show that T with X is an X. It can't be a T. But now that's no longer true anymore. So now we're talking about space-time symmetries. So what happens is two important things happen. One is that this fact no longer means that there's this is true. Now there can be a T on the other side. And that's not unrelated to the fact that space-time symmetries, coordinates, whether or not the symmetry is broken or not, how does the coordinate change under translation? What happens to a coordinate under translation? Shifts. Is that a linear transformation? No. So it doesn't matter if the symmetry is broken or not. The coordinates change nonlinearly, right? So if you break translations or not, It doesn't matter, right? We'll see in a second that we'll think about coordinates soon as Goldstone bosons. And so that's naturally, there'll be a relationship between the nonlinear transformations. So of course, when I write this, I'm leaving off the structure constants and the coefficients. This is supposed to be just a cartoon sketch saying that there's some element in x and some element in t. The numbers are not relevant. Okay, so and this is a consequence of the non-compactness and the lack of the ability to write the structure constants in a totally antisymmetric fashion. Okay. So how does this affect our how we parameterize the fluctuations around the vacuum? So if you remember, last time we said that we parameterize the fluctuations by looking at the broken generators, right? But now consistency requires that we actually exponentiate unbroken generators which transform nonlinearly. So the Coset construction for spacetime symmetries was first written down by in a set of papers by Volkov and Ojevetsky, which are two people you've probably never heard of. Well, maybe you've heard of Volkov because he was also the first one to really talk about supersymmetry. But this paper, I think, in my opinion, is a underappreciated, important piece of science. They're not the easiest papers to read. What they showed is that you can continue to follow the method of CCWZ if you extend it in the following way. I'm mainly going to be talking about the Galilean group as opposed to the Poincaré group. So every system in nature, like turning off gravity, is invariant under Poincaré transformations. And the Galilean group, why do we study then? Why bother studying systems which are invariant under Galilean symmetry? And the answer is some things are about it a little bit simpler, some things are about it a little bit more complicated. But typically when we look at a non-relativistic system, well, why do we look at what does that mean, a non-relativistic system? It means there exists some frame where everything in that, all the particles under study are moving slowly compared to the speed of light, right? So what that means implicitly is that there's stuff around. You're not working in the trivial vacuum, right? You've got particles, and they're moving slowly, and you're working at low energy, so you can't annihilate them or create them, right? In a non-relativistic system. So as high energy theorists, we're not usually trained to think about this, but if you have a non-relativistic system, there's an additional symmetry, which is particle number conservation, right? So if you're looking at a non-relativistic system, you have particle number conservation, and if you have particles around, those particles break all your space-time symmetries, right? So the vacuum of the system has a quantum number, which is the number of particles in the system, because you can't change that. So if you like, there's just as we talked about yesterday, there's a super selection rule, which tells you that if you're sitting in a vacuum with n particles, you will always be in the vacuum with n particles, and nothing can change that. But if you have n particles in your vacuum, that means your vacuum is breaking space-time symmetries because the particles are breaking the symmetries, right? So in high-energy physics, we typically always think about because particles can be created and annihilated. Well, the true vacuum state has no particles because that's the minimum number. That's the least state with least energy, right? But that's not true. So in Galilean symmetries, you automatically are always going to break boost invariance, right? Otherwise, it doesn't make sense to talk about Galilean symmetries. There has to be stuff. And once there's stuff, you break boost invariance. Okay? So, what I'm going to do is show you how to do the Coset construction in the context of the simplest example, which is a point particle. Right? So how do I break? There are lots of different ways of breaking space-time symmetries. I could put down a particle. I could put down a membrane. Right? Or I could fill space with a solid. Right? So those are three different possibilities of having one unit of it, something breaking space-time symmetries. Of course, I could have two particles or two membranes, but those are just trivial extensions of one particle or one membrane. So I have to be able to coordinatize the stuff that I've written down. So what we're going to do is we're going to look at Coset constructions for defects. That's typically what you call it. If you have a particle sitting there, that's a defect in space-time. Or if you have a membrane, a D-brane, or whatever you want to call it, that's a higher dimensional defect, right? So assume the existence of a defect in space-time, and we have to coordinatize it. So we'll give it some coordinates. We'll call it y, I of x and t, right? So y, I of x and t tell you where the defect is. If it's a point particle, it would be just, so if for a point particle, it would just be xi of t. Right, yi of t, if it were a two-dimensional, if it were a string, for instance, right, then x would be one coordinate telling you where you are on the string, coordinatizing the string. Or for a if we're a D brane, a D3 brane, then this would have two coordinates, so forth and so on. So we have to coordinatize the defect, and now the defect itself breaks in general. If it's a point particle, what symmetries will a point particle break? Translations and what else? Boosts. If it's a membrane that's flat, rotations, right? But how many translations in a flat D brane? So you're going to have two left over, and you'll break one. So what you choose for your defect will determine the symmetry breaking pattern. So what Volkov and Ojevetsky told us to do is we now have to parameterize our vacuum in the following way. So let me put an arrow here. So you take whatever internal symmetries, whatever else you had, and you multiply it by, you have to include now these factors. P twiddle are the unbroken translations. And P vector are the broken translations. Okay, so notice this x is the coordinate x. This x and this x are the same thing. And this t and this t are the same thing. Okay? This y now is starting to look like a Goldstone boson. Right?
Does it make sense to exchange two exponents or maybe?
So, okay, so one thing we didn't talk about yesterday is if you have multiple generators, you have a choice of how you write U, the order. And any choice you choose, the final physics won't matter. So you're free to choose. Well, these guys commute, but imagine I had some that don't commute. So for instance, since I'm doing, we know we're also going to break boosts, I'm going to have to write e to the I eta of k. And this eta now is the boost Goldstone boson. So eta This is the Booth-Goldstone boson. This is sometimes called the Fremon. Okay? So I could choose, now K, so let me write down the Galilean algebra for you. So the non-trivial commutators are Ki with Pj is I m delta ij. M is the mass of the particle, the mass of the object that you're looking at. M commutes with everything. That's sometimes called the central charge of the algebra. Okay? And then, of course, you still have angular momentum, Li with Lj is I epsilon ijk Lk. And you have the other non-trivial one is H with Ki is I pi. Let me make sure I get the sign right. Yes, that's right. And of course, Ki's transform also like vectors. So Li with Kj is I epsilon ijk k. H is the Hamiltonian for a free particle, right? So, yeah. So here I've assumed that the interactions are boost invariant. So whenever you write down the Galilean algebra, it's under the assumption that that's true. There are interesting things that happen when you start to write down non-trivial interactions, but we won't have time to talk about that. Yeah. No. Mm-mm. So this H will always obey this algebra. Okay, so now let's apply this to the point particle. Okay. So Coset construction for non-relativistic point particle. Okay, so the broken generators are going to be all the translations, right? All the boosts, and the unbroken are going to be the rotations, and the mass. So the mass is a generator, it's a central charge, and you could ask, how could you ever break the mass? And it turns out quantum mechanically that can happen, it happens in a superfluid. So that's when the number of particles becomes ambiguous. Okay, so let's calculate what the action is. So we know our formula, we know our formalism, we turn the crank, we get an answer. Okay, so let's turn, yeah. Yeah, those are these Galilean boosts case. Yeah. Okay. So here's our, so now let's modify our coset here. So now there are no unbroken translations, so that guy's gone. This y just becomes y of t. Okay, and let's move him over to make it look nice. Oh, and I should put in a minus sign here. I think the convention I use is always with a minus sign. Okay, but as usual, the energy and the momentum have opposite sign. So if you wanted to, you could write it like a 4 vector. This is u. So this goes u. Yeah. So I before I had the extra u in case there were other symmetries that were broken, but now that we know these are the only broken symmetries, we can put an equal sign. And this guy becomes function of t. Okay? Yeah. Pardon me? Y is the trajectory of the particle. Yep. 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 So it depends. So if you look, if you're expanding around a flat membrane, then you'll have two unbroken translations and one broken translation. So then you would have the two unbroken translations would get dotted into y here, and then I would have to have t would just have the unbroken translations. Sorry, I said it backwards. The unbroken translations would go here, and the broken ones would go there. But notice that I've broken all my translations, so the only thing with explicit coordinate dependence is the h. Okay, so now we do what we did before. We calculate the Mark-Cartan form. So I can erase this.
When you say that translations are broken, do you mean also time translations?
Time translations are not broken, right? So that's why there's still an explicit t here. Yeah. Does that make sense? So remember I said that all the unbroken guides get dotted into the coordinate. All the broken guides get dotted into the coordinate embedding of the defect. Right? This is the coordinate of the defect. This is just the coordinate.
But the particles has some dynamics, don't you break translation themselves?
So in order to break time translation, you would have to have some sort of explicit time dependence on the system. If I had an external force, that would break time translation. Something which didn't, so the Hamiltonian didn't commute with the Hamiltonian, right? Okay, so now we write down the Mohr-Cartan form, and now things are only a function of t. So the Mohr-Cartan form is going to be u minus 1 d by dt of u, because that's the only explicit coordinate dependence we have. Right? Because we're doing a point particle theory, and the only t dependence, the only coordinate dependence is t. Nothing depends on x or y, because nothing depends explicitly on any other coordinates. So now this is called a world line action. So if we were to write down, this makes sense, because if we were to write down an action, it would just, for a point particle, if there's an integral dt, there's no x. It's not a field, it's a particle. So everything only depends on t. So similarly, our Mohr-Cartan form only depends on t. Right? Okay, so what is this equal to now? Well, we still have the covariant derivative and the gauge field, and there's one additional piece to it, which in this case turns out to be trivial. And now I'm going to put in an I here. And I'll explain what this E here is in a second. Okay, so let's look at this. So these two pieces should look familiar. Right? Those are the covariant derivatives for the broken generators with the pions. This P0 piece is something that we didn't have before. And now there's this E here. This E is what's known as the Einbein. And the Einbein relates the time in an unboosted frame to the time in a boosted frame. So under G, we perform a boost. In general, time might change, but we know that's got to be 1 in a non-relative, because what happens to time under a Galilean boost? Nothing. So this Einbein we know non-relativistically is going to be 1, but if I were doing this relativistically, what is this Einbein going to be? Louder? Somebody? Right. It's going to be the time dilation factor. And if you do it right, when you pick off the coefficient of P0, that's exactly what you'll get. And so that's going to be a homework problem, is to work. Once I work out the non-relativistic case for you, I think it would be a good exercise to work out the relativistic case. So let's work out the non-relativistic case explicitly. So I'm going to do this step by step so that you can see, so that will allow you to do the relativistic case for yourself. Okay, so I'm going to let's extract the covariant derivatives. Okay, so let me write it all out. So I shouldn't have erased it. So let me leave it here. Make sure I do it the same way in my notes. Okay. Just so I think be consistent. So there's some arbitrariness in the choice of sign. It depends on your convention for whether or not a boost goes to V plus V delta V, or V goes to V minus delta V. So you have some choice in the sign. Of course, the final answer doesn't care what you do. Okay, so let's calculate this Einbein. So this thing is equal to U inverse, which is e to the minus I eta dot k, e to the plus I y t dot into p, e to the minus I ht, d by dt, okay, so let's concentrate on this piece here. Say again? This is this. Right? Okay. Oh, just so I could agree with my notes. You can choose it to be whatever you want. I just chose it to this one because that's the way I did it when I worked it out, and now I want to be consistent so I can check to see if I got the answer right. Feel free to use your own convention. Okay, so what is this equal to? So this gives us IHT all right, I'm going to be highly redundant here and rewriting things all the time, but maybe for the sake of clarity, that's okay. So I'm rewriting this bracket. Yeah. Oh, thank you. Yep. Okay. Everybody happy with this? Okay. So now, one good thing is we don't need to use the trick equation because all the k's commute with each other. So I can push this through any way I want. But I have to be careful in other spots because H and K don't commute. Let me leave this here. Okay, so this, just so you don't get confused, that's what those brackets become. So the H commutes with itself, so I can kill this. H commutes with P, so I can kill that. So the only thing I can't push it through is the boosts. Yep. Let me check, possibly. In the second term, this one. Oh, yeah, the EVIH, e to the y. Wish I could just click and drag this. I have to rewrite it. Okay. Okay, so see what happened in the first term. I can push this through and cancel it. Right? I can push this through and cancel it because P commutes with H, but I can't push the K through the H because K doesn't commute with H. Right? So that's the first term. Now let's look at the second term. So this guy obviously cancels with this guy. This guy I can push through, but I can't push through the boosts. Right? And finally on this term, everything is nice and simple because this cancels with this cancels with this. K commutes with itself. So all I'm left over with is okay. Okay, so now we're going to equate it with this. So what happens to e to the minus ikh, e to the ikh, e to the, e to the minus I eta? This is just a boost on H, right? This is how H would get transformed under a boost transformation. So this just becomes okay, so this is a boost by a velocity parameter, which is eta, right? So how does p squared over 2m change? Well, with my conventions, p goes to p minus eta. So h p squared plus 2m is just going to get a factor of minus p dot eta, and then a 1/2 m eta squared. That's just how an energy changes under a boost by v. Does everyone understand that? So I could use my magic formula that I showed you at the beginning of class, or I could just be smart, which is always better, right? Because then I don't have to do other calculations. I know how energy changes under boost. That's how it changes. P squared over 2m, yeah. Okay, and now here, this P, also we know how it changes by boost. This becomes minus I y dot of t dotted into p minus eta. And this just becomes plus I eta dot k. Okay, so now we've done all the hard work, and now we can compare this object with this object. So P0, remember, is H. So the first thing we realize is E is equal to 1, so that's a sanity check, right? Time doesn't transform under a Galilean boost. Remember, E is the thing that relates the boosted and the unboosted frames. Okay, so E is equal to 1. Let's pull out The, I forgot in here, I also have plus m a0. Right? M is an unbroken generator, and the coefficient of the unbroken generator is the gauge field. Okay? So let's pull out the coefficient of A0. So that's the coefficient of M. Let me just. Oh, and I forgot an M here. I knew something was wrong. So P, remember, under a boost, P goes to P minus M eta. So there has to be an M there. Okay. So now we can read off A0. So A0 is 1/2 eta squared, right? Because there's a coefficient of, that's here, the coefficient of M. And then there is a plus a y dot into eta. Everybody understand that? Third term in here? First bracket. This line. 1/2 m eta squared. Yeah, because if I take p squared over 2m and I make this transformation, then I'm going to get that last term. Okay, so now we've extracted the gauge field, we've extracted the Vierbein. Now let's extract the covariant derivatives. So the covariant derivative of the Fremon we can read off from the coefficient of k. So d on eta a is eta dot a. And d on pi is the coefficient of p, which is y dot plus eta dot. I guess it's an overall minus sign. Okay. So the analog of the pion now is this linear combination of y dot and eta dot. No, there's no dot on the eta, right? No, there's no dot on the eta, sorry. Okay. Now what do we do? So we followed the mathematics. This is what it's told us is going on, and we can form invariance. But we stopped to think for a second, and we realized there's something weird going on. And that is, okay, I could write down invariance, and I've got this y, degree of freedom, makes sense. Y is the position of the particle. So we can get an action function of y. But what is this eta thing? Right? I've never seen an eta in any other degree of freedom when I describe a point particle. So there's something wrong. We're not doing something right. And the answer is that the eta is what's known as a redundant Goldstone boson. So if you remember what when we derived Goldstone's theorem in the non-relativistic limit, we showed that there need not be a actual particle or a degree of freedom corresponding to every broken symmetry. So this eta shouldn't be in the theory, and the question is, how do we make sense of it to get the answer right? So let's first pause for a second and try to understand why we have this redundancy. So as I'm going to show you in a second, when you break space-time symmetries, many of what you thought was a broken symmetry, Goldstone boson, is not independent of other Goldstone bosons. And let me give you the sort of classic simplest example. So suppose I have a brain, right, that goes into the board. So it breaks translational and rotational invariance, right? So there should be a translational Goldstone corresponding to shifts in this direction, and there should be a rotational Goldstone corresponding to rotations, right? So let's consider a small rotation of the system. I rotate the system by the action of a Goldstone fluctuation, right? So a fluctuation in the Goldstone corresponds to the Goldstone is just the rotation of the system. But remember, Goldstone bosons are local objects, so I could equally well reach the same state of the system by making a local translation. So I translate here by this amount. And you can see I can achieve a rotation by a local translation. So rotations and translations, once I make them local, are not independent of each other. Okay? This redundancy is sometimes called the inverse Higgs mechanism. And I think that's probably not the best term for it. So why is it called the inverse Higgs mechanism? Well, the Higgs mechanism is a way we get rid of Goldstones, right? By eating them into the gauge fields. Here we're getting rid of Goldstones, but we're not getting rid of them. They're actually redundant degrees of freedom. So it's related in the sense that you're getting rid of Goldstones, but the physics is very different. So how do we get rid of the Goldstone boson? How do we get rid of this eta? What we're saying is that the boost is this boost Goldstone is a redundant degree of freedom. And the way this is done is we impose a constraint on the system, but we have to impose a constraint which is consistent with the symmetries. So to remove the redundant Goldstones, we impose a constraint. And that constraint must be consistent with the symmetries. Okay? So what constraint could I impose that would be consistent with the symmetries? Well, I could just set one of these covariant derivatives to 0. Right? And since it transforms covariantly, if it's 0, then the transform of it will also be 0. That's what it means to impose a constraint which is consistent with the symmetries. So what we're going to do is we're going to say d pi is equal to 0. And that's called the inverse Higgs constraint. So what this tells us is that y dot is equal to eta. Yeah. I think that got erased. There should have been a dot on there for wasn't there before. So the covariant derivative of the eta is the coefficient of Ka. And that's eta, that's the eta dot. I think that dot that was there. Okay, signs. So this, yeah, the dot is missing here. No, I think that sign is correct. Middle of blackboard here. Middle blackboard here. So let's see. So the coefficient, the first p is plus y. Yeah. So this one is plus. So I guess they should both be plus. It doesn't really matter for reasons that you can see because it's 0. So yeah. Yeah. I see what you're saying here. Yeah. This also isn't going to matter. So you can sort of see what's going on here. Yeah. Yeah. Right. So what this is telling you is, what is the boost necessary to go into the rest frame of the particle? It's just the velocity of the particle. Right? That's what this is saying. That's why the boost is sort of redundant. Okay, so we have, so this also tells us that d eta is y double dot with a minus sign if you like. Okay, and now let's build an action. Yeah. So if you have a massless particle, you gotta work. Yeah, things get tricky in that case, but you certainly can't do the Galilean algebra. That's for sure. But when you have a massless particle, things get a little bit trickier. But can't really go into that right now. We can talk about it offline. Right, exactly. Yeah, for sure. Yeah. How do you, oh, good. I'm glad you asked that. So in general, how do you know when there exists an inverse Higgs constraint? So now let me tell you before I do that, let me finish this and then we'll come back to that. Let's write down the action for the point particle. So we're almost there. So you'll see why the sign doesn't matter in a second. Okay, so what is the action? Well, we have to write something down which is invariant under H. And what is H in this case? What's the only unbroken symmetry? And rotations. So all I have to do is write down anything rotationally invariant, boom, we're done. Okay? So, well, what can we write down? Well, we've already said that this is 0, so we can't use that anymore. This is all we have left. So the only thing we can write down is our action, which is now an integral over dt, is some number, we'll call it C1, times d eta a squared. That doesn't look anything like what I know as a point particle action. And in fact, it doesn't even make sense. Okay? So, what time is this supposed to be over? One o'clock. Okay. We started at 11:30 or 11:15? 1, okay. This opens up another can of worms, which I would now like to share with you. So this is going to seem like a small tangent, and then we're going to come back. So let me pose the following question to you. Why is it that everything we learn in physics is described by a differential equation which is second order in time? Even, classical mechanics. What if I had a free particle? You would need more initial data. That's true. So there are two, that is a loaded question that I asked you. First of all, why is nature described by differential equations? Why couldn't it be an integral equation? Second of all, why is it always a second order in time differential equation? So this is something that we don't stop to think about, but that's kind of odd, don't you think? Why, I mean, that's pretty peculiar. Why does that have to be true? Yeah. So the locality is the reason why it's a differential equation and not an integral equation. So if you had an action which was non-local, like the one, if I wrote it down as an integral over d4x, d4y, so that there was action at a distance, and I applied Euler-Lagrange equations, I would get a integral equation, right? But because it's local, you get a differential equation. So that is the correct answer to the first half of the problem. Now what about the second half? Okay, so almost that. So there's a little-known theorem by Ostrogradsky, if I pronounce it correctly, which was actually Ostrogradsky is someone you've probably never heard of, but he was the first one to write down the divergence theorem before Gauss did, right? But nonetheless, it's called the Gauss's theorem, or Gauss equation. And what Ostrogradsky showed, this is in the 1840s or 1830s, is that any Hamiltonian system which is based on a higher order time derivative beyond 2 is inherently unstable. Okay, and there's a very nice article by Richard Woodard discussing this, and he even talks a little about the history of Ostrogradsky. It's very interesting. So let me give you and it's really fun to read, and I think you'll enjoy reading it. Let me give you the archive number. I think it's not unrelated to that. So certainly, like gravity theories, gravitational theory, massive gravity theories, often suffer from these Ostrogradsky instabilities. So let me give you the archive number. Okay, here it is. So Ostrogradsky's theorem. So the archive is 1506 0221. That's definitely worth reading. Okay, so now we have a problem because this action clearly would violate Ostrogradsky's theorem, right? It's a higher order. This is going to be a fourth order in time. Yeah. Yeah, so there'll be linear instabilities is the exact statement of the proof of the theorem. Such systems. There are other caveats as well. So this we've got a problem because this is not acceptable. But before we explain why it's not acceptable and how to fix it, we have to talk about one other thing. So one of the basic tenets of effective field theory is that you should write down everything that's possible. So if a higher derivative term is possible, you should write it down. So and I seem to have an issue. Okay? So how do we avoid that? In other words, when we wrote down a theory of pions, we can include as many derivatives as we want. As a higher dimensional operator could have 20 derivatives, right? Then it seems to violate Ostrogradsky's theorem. Yeah. Yeah. So I actually wasn't going to say it like that. Let me come back to that in a second. But the point is, in the effective theory, you're going to treat those as perturbations, right? They're subleading because they correspond to higher dimensional operators. So as long as you treat the higher order time derivatives as perturbations, then that's perfectly fine, right? In perturbation theory. The problem is, so a good way to see that you're going to run into problems is if you try to write down a propagator, which is higher order in time derivatives, will have higher orders in energy, and that's going to give you all sorts of new poles. And so for those of you who've taken field theory, know that the poles correspond to on-shell particles propagating in your system. But now I've got fourth order poles, and you have to make sense of that. You run into unitarity problems and all sorts of issues like that. So that's assuming you're treating that higher order derivative as a leading order term, so it shows up in the propagator, right? But if you treat it as a perturbation, it only shows up in the numerator. So everything is fine. You can also remove them higher order derivatives by redefining the fields. But I do want to get into that. Okay, so that means that there's nothing wrong with this being here. It's just that we need something which is leading order. So if we're going to keep this here in the theory, that's fine as long as it's a subleading term. So notice by dimensional grounds, what is this? This C is going to have to go like some scale, some power of the cutoff of where the theory breaks down. So interesting question is, what do you think the cutoff, where would this theory break down? At what sort of time scales or what sort of length scales would this theory break down? What's the starting assumption that was implicit that we never actually even talked about, that I didn't mention once? Non-relativistic, that's true, but what else? Yep. Yep, all correct, but there's still one crucial thing. I assumed it was a point particle, right? It doesn't have any, so a point particle has no internal dynamics, right? If I'm going to treat this chalk as a point particle, I'm only allowed to look at it at scales much larger than the size of the chalk. So if I were to write down an effective field theory for this piece of chalk, what is the breakdown scale going to be? I think that's right, but I didn't understand it. The inverse size of the chalk, right? So every higher dimensional operator in this theory should be suppressed by some scale which is set by the size of the particle, right? I can't treat it as a point particle is an approximation. There's no such thing as an exact point particle, even an electron, right? So all higher dimensional operators will be suppressed by the size of the particle, or to get the right units based on the size of the particle, right? So we can work out the units here, but this thing's going to be down by some power. Let's call R the size of the particle. We'll put an N here, and you can work the units out for yourself. Or sorry, it should be upstairs, sorry. So that when R gets really small, it becomes irrelevant. Okay? So the question is how we're still missing 1/2 mv squared. Where is 1/2 mv squared? Yes. Good. So why is A0 okay to write down? That's true, but A0 is not an invariant, right? How does A0 transform under a G transformation? What is A? How does it transform? As a gauge field. How does the gauge field transform? Under a gauge transformation? It shifts by a derivative. And A0 will go to A0 plus d by dt of the gauge function. That's a total derivative in one dimension. So what I'm allowed some other number times a of 0 dt, and that is an allowed invariant. It's not invariant, it's invariant up to a total derivative, right? So under a boost, it's going to go under a general G transformation. It's going to shift by a total derivative. But that's okay because total derivatives don't affect the equations of motion. So yesterday, when we talked about once you have all your geometric objects, what can you write down? I said, well, write down anything which is H invariant. That's not general enough. You have to allow for objects which transform as total derivatives under G's. Right? That's called the West-Zumino term. Because this is an example of a West-Zumino term. So those of you who are familiar with the Cairo-Lagrangian know about West-Zumino terms, and they have interesting cohomological structures and topology involved, which usually when you have a compact groups, in the space-time case it's not so interesting. But there's a whole mechanism for writing down. So here we were able to guess the West-Zumino term because someone realized, oh, A0 is just going to transform like a total derivative, right? But in general, there's a whole methodology for constructing West-Zumino terms that we won't have time to go into. Okay, so good. So what is A0? It's eta dot squared, right? But it's eta squared, and eta squared is y dot squared. So ta-da, we just spent a day and a half deriving 1/2 mv squared. I don't expect applause, but some appreciation would be nice. Okay. So now let's write down our action. So A0, once we replace y dot by minus eta, this becomes minus 1/2 eta squared. So, but there's an unknown coefficient C2, so I can just write the action as C2 times 8 y dot squared plus C1 times y double dot of a squared. And we can write down more and more terms if we wanted. Okay, so we have to fix these C1s and C2s. We don't know what they are in general. And so we have to fix them using an experiment. Okay, so the leading order equations of motion is m y double dot is 0. And if we did an experiment or C1, we would extract that C1 is 1/2 m or C2, right? So C2 is 1/2 m. So what is C1? And what is the meaning of this term? It's an acceleration squared term in the action. So what could that possibly mean? So if I have an object which is of finite size, it's not going to obey Newton's laws anymore, right? It takes a finite amount of time for information to propagate from, let's say it's a ball. If I push it here, right, then it's going to take a finite amount of time for that to reach the other end, because it's not really a point particle, right? That's an example of a finite size effect. So the way in which the particle accelerates isn't the way a normal particle accelerates because it's of finite size. So if I push it, and the way its inertia behaves will also be different. So let's work out the dimensional analysis and figure out what's going on here. So this is S, and there's a dt here. And let's figure out what the units are of C1 and see if we can make some physical guess as to what parameters will fix C1, or what parameters C1 will depend upon. Okay, so S has the units of angular momentum, right, which is length for x, and then mass times velocity, which is length divided by time. So this goes like m L squared t. Okay, so if we, so this, we're going to replace this now by 1/2 m. And so now let's look at C1. So this guy, so y double dot squared, when I write brackets, that means units. So the units of y double dot squared is length squared time to the 4th, right? So that means that C1 must have the units of, so we pick up a t here. So C1 has to have the units of times squared mass. Is that right? So I have the d. I have to, don't forget to count the dt. So that's going to kill one of the times. So I think it should be time 4, and we're trying to get to 1 over time. So t squared t minus 2. Is that right? No, hold on. No, t upstairs, right? Because this thing's downstairs. Length squared dt squared, right? Everybody happy with that? Okay. So mass C1 has units of mass times time squared. So how could we get a time from the system? Well, the only sort of relevant time scale would be the time it takes a signal to cross from one side to the other, right? So there's going to be some intrinsic velocity corresponding, say, the speed of sound, which is how fast a pressure wave can travel, right? So it's natural to think that t goes like the radius of the particle over the speed of sound, right? So C1 is going to go something like radius squared mass over the speed of sound. Right? And if we wanted to, we could trade that mass for a density if we assumed it was uniform density and a radius. So we could see that when the radius gets small, this effect goes away. Right? Or speed of sound squared, yeah. And also when the speed of sound gets, what's going to happen as the speed of sound gets larger? Is the effect going to get smaller? Would you expect it to get smaller? The finite size effect to get smaller or bigger as the speed of sound gets larger? So, right. Because in the limit where we're instantaneous, it would behave just like a point particle. Right? So it takes some time to propagate from one side or the other. Good. So that's an example of a finite size effect. And in fact, when we talk about black holes and LIGO, this is actually, I realize this is incredibly rudimentary to some of you, but this is actually going to play an important role when we talk about something very important. So it's important that you understand it. Yeah. Yep. 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 You could solve. No. So you would treat this as a perturbation. So you would take the first order equation, you'd solve your leading order equation, you'd plug it back into here, and then you would solve the next one and so forth and so on. You would do it iteratively like you would in perturbation theory. Okay, so one interesting question is to ask, when does this effective field theory break down? Well, it should certainly break down when this piece starts to be of the same order as this piece. Yeah. The speed of sound, yeah, in principle you could tune it, yeah. And then, right. So look, if you've got a really squishy object, and I hit it, it's like jello. the point particle approximations could be really bad, unless you look at it over very, very long time scales, right? Right, exactly. Let's hold off on that question. Okay. Yeah. Oh, that was just talking about quantum mechanically. Yeah. I'm doing everything classically here at this point. Yep. Sure it is. Sound waves are just classical. I mean, I can elevate this to a theory of quantum mechanics, but then it becomes really things get complicated when you do that. Because in quantum mechanics, we treat the electron as a point particle because it is a point particle. When does an electron not behave like a point particle? When you probe it with energy so that you can do particle creation. But as soon as you do particle creation, you've got to go to a field theory, the world line theory, although you could use Feynman tricks to try to fix it up. But as soon as you have particle creation, you can't just talk about the action for a particle anymore. You have to do field theory. You don't have to, but that's the way we do things usually. Yes, that's how quantum mechanics cures it, is that once you start probing things on the wavelength of the electron, de Broglie wavelength, then it's a Compton wavelength. Okay, good. Now let's do 2-point particles. We're going to work our way up to Avogadro's number. Okay? So why is the point particle like a Goldstone boson? Because there's no gap. It's a gapless object. E is p squared over 2m, right? So I promised you that the symmetry breaking pattern would give us the answer, would give us the degrees of freedom, which it did, and it would give us the action, which it did. So I've kept my promise. But now we need to push a little bit further because that's just a little too trivial. Okay, so suppose I do the next best thing and I do 2-point particles. Well, that's kind of just trivial because if they don't interact with each other, we know it's just the action for 2 free particles. But suppose I wanted to describe a system where there's a spring, and you can make it any force law you want, that connects the 2 particles. And let's see if our claim still holds. So the claim is, if you tell me the symmetry breaking properties of the system and the symmetries of the system, then I can determine A, what are the degrees of freedom, and B, what is the action. Let's see if that holds true now. Okay, so this system will have, since we know the answer, will have, will it have a gapless mode? What will that gapless mode be? The translation of the whole system. Just take it and move it. Right? E is equal to p squared over 2m. If I treat the thing like a point particle itself, it's just a point particle. But I also have this degree of freedom. That is a gap degree of freedom. So that is omega. So there's one gapless degree of freedom where omega is k squared over 2m, where m is the mass of the entire system. And there's one where omega, let me call the spring constant big K. is the square root of big K over m. It doesn't depend on K, the momentum. There is no notion of K, right? It's just omega is equal to K. That's a gap, right? So I can't describe that using Goldstone's theorem because it's gapped and I can only describe gapless things, right? So remember, a gapless system is when omega is equal to K. K is the momentum. Now, it makes sense to talk about the momentum of the particle of the object moving. It kind of makes sense that whereas this thing you don't talk about any sort of momentum. It's just there's no frequency momentum relationship. The frequency is just fixed to be the oscillatory frequency of the spring. Okay? So what I'm going to do later is add an infinite number of springs and show you that when you add an infinite number of springs, there are more gapless modes, and those gapless modes will correspond to phonons. But if you have a finite number of degrees of freedom, there's no gapless modes, and the only gapless mode is the translational mode. But there's one other gapless mode. What's the other gapless mode? Rotations, right? So if I'm only considered with gapless excitations, we have 3 translations and 3 rotations. Okay? So let us apply our formalism to the system. Yes, these are broken and the boosts are broken. And in principle, there are boost Goldstones, so you're absolutely right, but we know that they're going to be inverse Higgsed, right? So here, I wasn't being sophisticated. I was just saying, okay, anybody knows from basic undergraduate physics that if you have a thing, it can rotate and it can translate, and no one's going to think, well, it could also boost, and that wouldn't make any sense. And that's consistent with the fact, now that we're more sophisticated and we use these Coset methods, that the boost doesn't really exist, right? So, but we shouldn't put that in by hand. It should follow from the mathematics. Okay? So it will indeed follow from the mathematics. So let's write down our Coset construction. Yeah, so actually, so that's right. You have one, you're right. In this particular case, in three dimensions, you'll have one rotational will be unbroken. That's the rotation around this direction. But I actually wanted to do it in fewer. Okay, let's do it in 3 dimensions. I was going to do it in fewer dimensions. Let's do it in 3 dimensions. So let's write down. So let's build our Coset construction. Okay, so let's write down our U. And I chose like this. And I'm going to call the Goldstone boson for rotations theta. Okay? So since I'm running out of time and the process is exactly as it was before, I'm just going to write the answer down. So again, we calculate remember the algorithm is calculate more Cartan form. And this, again, E, which is going to be 1 again, is now going to have H0 okay? And the calculation goes through exactly as it did before. But now let me tell you what everything looks like. So d pi a is eta a plus ya. A0 is the same as it was before. Now we have d theta I is theta dot. And what changes a little bit is d eta. So d eta I becomes minus eta dot I plus epsilon ijk eta j theta k. Okay? So, so the point particle is what it is before. So we have our inverse Higgs constraint, which is the same as it was before. And I'm going to get now, before we finish, I'm going to tell you how to know when there's an inverse Higgs constraint. So I'm going to set d pi to 0, which is again going to tell us that y dot is eta. But now I have an action, which I can write down. So what is the action? Good. What is h in this case? Yeah. So let's assume that. Let me assume that there was no rotational symmetry at all. Assume they were all broken. So I can draw a spring that looks like this. Okay. Now we've got rid of that extra problem. Okay. So what are the so h is what? There's nothing, right? Rotations are broken, so I don't have to write down a rotational invariant action if I don't want to. It only has to be invariant under h. So S is, it can be anything you want it to be. Because we've said that we can't account for the internal dynamics, right? So we have to, we're only looking at we're treating it as if it's a point particle, right? Except we have rotational degrees of freedom. So now I have 1/2 m y dot squared plus theta I theta j, because it doesn't have to be rotational invariant. So I can weight this I and j any way I want with some arbitrary constants. I don't know what they are. There's some arbitrary constants. But let me call those constants, I don't know, ij. So what do you think those constants are going to be? It's the moment of inertia tensor, right? So you have to fix that by an experiment. But what's interesting now is I can write down couplings between the rotational and the translational degrees of freedom, right? So I can start to write down nonlinear effects, and the form of those nonlinear effects is going to be determined by how by the Wilson coefficients of those functions. So so for instance, I can write down, here's a nonlinear effect I can write down, which is d eta I squared. So consider a nonlinear effect. I could try, so for instance, I could write down d eta I. Now, because remember, it doesn't have to be rotationally invariant, and I could just put a ci here in front of it. So this term won't be very interesting because it's a total derivative. So I can just ignore it if I were to write down dA to I. Right? Let's see, so D. No, H is still there. Here. H. Oh, yeah. H is nothing. Yes, because it doesn't have to be rotationally invariant. The thing is, it's not terribly interesting because this piece is a total derivative. Actually, I'm a little bit, something a little bit funny going on here because changes sign. I think I'm missing a time derivative. X, so this Y, I'm sorry, so, right, so this eta we know is actually Y dot, and this is Y double dot, right? There's something funny because I'm worried about time reversal invariance. So one thing we still have is we have H invariance, which means there should be time reversal invariance. So we're not allowed to write down terms which are not invariant under time reversal. And I'm concerned because these two terms seem to not transform in the same way under time reversal. So I think I'm missing a dot. So, okay, I'll fix that at the beginning of the next lecture. So let's come back to this. But before we close today, I want to tell you, I promised I would tell you when inverse Higgs constraints exist. So the condition for an inverse Higgs constraint is that if you have a broken generator, its commutator with an unbroken translation gives you another broken generator. So these P bars are these unbroken translations. So physically, what this means is essentially you can trade a translation for another generator. So let's look at the example of the so let's look at the example of the rotated this case here. Right? So here the broken symmetries were translations and rotations. Oops. Call that L. And also the boosts. And so the question is, if I have a unbroken translation, which in this case would say be a translation along this direction, if I rotate it with L, it will give me a broken translation. Right? So L with P gives me another P but rotated, because remember L generates rotations. So it'll take an unbroken one, turn it into a broken one, which is what this criteria is telling you. right? So let's see in the point particle, how do we understand why the Boost Goldstone's not there? So consider a point particle. So this is example 1, but let's consider a point particle. In that case, we have H, which is an unbroken translation. So let me write it in the same way. K is a broken generator. That's our X. H is an unbroken translation, right? P is a broken translation, X prime. And what that's telling you is that this guy's Goldstone is unnecessary. Okay? So that's the condition for breaking of translational invariance. So I didn't get as far as I had hoped to. Next time I want to talk about this nonlinearities, which tells you how the rotational and translational degrees of freedom interact with each other. And then if I have time, I'll do the solids, and then we'll start talking about black holes. So I'll probably do half the lecture next time on finishing this, and then the other half we'll do black holes.